In this video, I'm going to give you some tips for solving the ALEKS problem called identifying a molecule from its electrostatic potential map. This is actually a pretty tricky problem. It's a lot harder than it seems like it should be. So for this problem, we've been given a list of 5 molecules, and our job is to determine which of these 5 molecules could be represented by this electrostatic potential map, which is just like a bubble diagram of a molecule. And notice that it is possible that more than one of these is going to be the correct answer. So what I'm going to do is kind of give you a strategy walking through this analysis, starting with the easiest things that you can look at and moving my way up to the most complicated things that you can analyze. And you may not need to go through all of these steps to answer the question, but all of these steps should help you answer every single possible version of this problem. So the first thing that we're going to do is analyze the number of atoms that are represented by the electrostatic potential map. In this is kind of like a three-dimensional representation of a molecule, and every atom in the molecule is represented by a blob, a sphere that has kind of been shoved together. So this little blob right here, that represents one atom, and this represents another atom as well. Basically, this is saying here was atom number 1 and here was atom number 2, and then those two atoms just got kind of mooshed together to make this molecule right here. So what you're going to do is just figure out how many lumps or blobs you have. That corresponds to the number of atoms that you have in your molecule. My molecule has 2 different atoms because I've got these 2 different blobs. What we're going to do next is take a look at the possible molecules that we have, and we're going to eliminate anything that doesn't have the correct number of atoms. I have this NO2 molecule that has 3 atoms in it, and so that is not a possibility for this problem. If I had 3 atoms, if I had a molecule that had 3 atoms, I would see something that had 3 lumps in it, maybe looking like that. If I had something with 4, maybe it would look like this. Now, if you do have an electrostatic potential map that has 3 or 4 or more atoms in it, it might be useful for you to go to the internet and look up the Lewis structures of all of these different possible molecules. The arrangement of atoms in the Lewis structure should also match the arrangement of the blobs in the electrostatic potential. So again, if you have 3 or more atoms in your electrostatic potential, maybe consider looking up the Lewis structures of all of your possible molecules. Okay, so that's the easiest thing that we can do. The next easiest thing that we can do is take a look at the symmetry of our electrostatic potential map. And when we're looking at symmetry, I want you to look at the relative sizes of the atoms and also the color coding as well. So what I see when I look at this is asymmetry. I see one small atom and one larger atom, and I see one blue and one red. And that tells me that I have not just 2 atoms, but I have 2 different atoms in this molecule. And so that means I can go through my list again and I can eliminate. I know that I have 2 different atoms, so I don't have Cl2 because that's 2 identical atoms. I also don't have Br2 because that's 2 identical atoms. So if I had Cl2 or Br2, I would see something that looked like this, where the 2 spheres or blobs were the same size, and I would also see them having the same shading, probably no shading at all. And this is still going to be helpful if you're looking at a molecule that has 3 or 4 atoms in it, because you might see something that looks like this. This would be a molecule that has 4 atoms, and it looks like these 2 are pretty much the same size, so they're probably identical, and these 2 look like the same size, so they're probably identical as well. And so this analysis is going to be really helpful in terms of narrowing things down. Now, you might be tempted to say, we've done it, ta-da, we've found 2 molecules that have 2 different atoms in it, and they're both possible chemical formulas, but unfortunately, this is where the ALEKS problem has the potential to get really tricky. Now, maybe for your problem at this point, you've got the answer figured out. Maybe you've got it narrowed down to just one thing. But if you have more than one possible chemical formula, you need to continue analyzing your electrostatic potential map in terms of size of the different atoms, and also in terms of their relative charge distribution. So on this electrostatic potential, I have 2 different atoms. We've already talked about that. One of them is smaller than the other. So I've got a small atom and I have a big atom, relatively speaking. And my small atom is the one that is positively charged because it's blue, which is represented by, blue represents the positive charge, and my big atom is negative. Okay, so here's where we're going to need our periodic table. The periodic table reminds us, or helps us be reminded of the trend of electronegativity. We know that for electronegativity increases as we go from left to right. It increases as we go from bottom to top. So the atoms that are on the right-hand side and atoms that are on the top are more electronegative. They're going to be the ones that are more negatively charged. And if we take a look at our two possible molecules, we have the ClF molecule and then we have the HCl molecule. We can identify of these which one is the more negative and which is more positive based on their locations on the periodic table. For ClF, which is right here, because fluorine is on top of chlorine on the periodic table, that means that fluorine is the one that is going to be more negatively charged and chlorine will be positively charged. And if we're taking a look at the color coding in this, negatively charged atoms are going to be represented as red and the positively charged atoms are going to be represented by blue. Now let's do the same thing for HCl. Here's hydrogen and here's chlorine. As we go from left to right, chlorine is on the right hand side, which means chlorine is the one that is more negative. Hydrogen is the one that is more positive. Positive is blue and chlorine is red. Now, how is this going to help us at all? Because this representation has one positive and one negative, and so do both of these. But notice that the positive portion of our molecule is the smaller of the two. So what we need to do is make sure for these molecules, we need to make sure that the positive portion of the molecule is smaller than the negative portion. We need to make sure that the positively charged atom is smaller than the negatively charged atom. And we're going to go back to the periodic table again to think about the trend in size. So in terms of size, as you go down the periodic table, the atoms get larger and larger and larger. And this is true not just for atoms that are in the same column, it's just in terms of looking at the different rows on the periodic table. So for chlorine, fluorine, back to chlorine, fluorine. As you go down the periodic table, the atoms get larger. So that means that chlorine is larger than fluorine. So chlorine is our big atom and fluorine is our small atom in this particular molecule. And look, this is not matching up with the electrostatic potential. In this diagram, our small atom is the one that is positively charged, but in the ClF molecule, the small atom is going to be the one that's negatively charged. So I know that that is not the correct answer. And that leaves me with just one choice. So I know that HCl is correct, but let's also analyze the size for the HCl molecule as well. A hydrogen is in row number 1 and chlorine is in row number 3. So that means chlorine is the larger of the two and hydrogen is the smaller of the two. And take a look at how this matches up with the electrostatic potential. The smaller atom is the one that is positively charged. Good luck with this problem. It is tricky.